Hello, I'm Dong-hee Jung, an assistant professor in Korea University. Today, I'm going to talk about urban water system, especially water distribution system, the system's resilience and forensic engineering. This is outline of my talk. After briefly sharing some background, I will introduce some approaches developed to improve water distribution system resilience. First for pipe burst detection, and second for water distribution system design. I'm going to finalize my presentation by introducing forensic engineering and funded research project with the topic and will deliver some potential future studies finally. Let me define the resilience first. Researchers in NSF EPRI Regime project, Emerging Frontiers in Research and Innovation Program, Resilient and Sustainable Infrastructure, who are from various engineering domains such as water, transportation, communication, etc., they sit down together to have this generalized definition of resilience. So resilience is a system's ability. So the system can be water distribution system, transportation system, etc. And it is system's ability to gracefully degrade and subsequently recover from potentially catastrophic disturbances. So it is relevant to system performances in pre and post failure condition. Therefore, many studies on resilience found that this resilience cannot be quantified or described by a single measure or characteristic, but by multidimensional and multiple measures. Most commonly accepted subcomponents of resilience are so-called 4Rs, which are robustness, redundancy, rapidity, and resourcefulness. While the first two is related to system performance in pre-failure condition and at the failure state, the later two are about post-failure system performances. Two different research branches that are introduced today are first, data-driven pipe burst detection, and second, water distribution system design using resilience and robustness measure. Part 1, data-driven water distribution pipe burst detection. Pipe burst is a rupture of a pipe from pipe deterioration, high pressure, and ground shift from temperature changes and earthquake. Pipe bursts cause water loss out of the system. Since most pipe bursts cannot be recognized over the ground, customers and water users, they keep using their demand, which results in the increases in pipe flow rate and head losses. With the increased head losses, we have low pressure at customer tap and degradation of system functionality. This service interruption should be rapidly detected to avoid any collateral damage such as sinkhole. Data-driven detection method identify pipe bursts by monitoring pipe flow and pressure measurement collected from measuring device installed throughout the system. And this is most widely used method for pipe burst detection. Example of other method is water balance method that compares the sum of inflow and total water usage or withdrawal of a district, which require a month's time scale at least. In 2017, Professor Liu summarized data-driven approaches published in Quality Journal, where you can see diverse approaches. For example, artificial neural network, statistical process control method, and karma filter-based method. In this talk, I'm going to introduce total 3 sequential studies that I conducted so far, including these 2 studies. In the first study, I compared total 7 SPC methods with respect to their detection effectiveness and efficiency. SPC method utilize statistical theory to identify any non-random patterns in quality characteristic, here pipe flow and pressure, by comparing measurements and historical mean and variance later obtained under normal condition. We compare them in real-life data collected from a system in Netherlands and also in synthetically generated data from Austin network. The results show that univariate method with a long memory of past data, for example, cumulative sum method, better perform than multivariate method. Here, univariate method applies statistical rules to individual mirror data independently, while multivariate method use correlation information among different mirror data. Basis of SPC method is the control chart that consists of time-varying mean as the center line and control limit constructed by mean plus minus some multiples of sigma. For example, as you can see from the top figure, under 4 sigma control rules, if any measurement falls beyond the limit, it assumes there's a burst. However, measurements can fall beyond the limits even without burst. As you can see from the bottom figure, for example, pipe flow values can be shifted up here by operational changes, such as source pipe, valve closure, or additional pump operation. An alternative to avoid such a false alarm is to construct control chart for each single potential operational condition, which is often very challenging. Enough data would not be collected to perform a statistical analysis for certain operational condition. To overcome the limitation, we propose a Kalman filter-based pipe burst detection method. Kalman filter is a state estimator from which nodal group demand can be predicted or estimated by using directly measurable variable in water distribution system, such as pipe flow and pressure. In estimating nodal group demand, Kalman filter can consider any operational and boundary condition change in exogenous variable, so there's a mechanism to consider that in the method. Estimated nodal group demands are then disaggregated into nodal demands, by which a network hydraulic simulation is performed to obtain nodal pressure and pipe flow rate. These are estimated value and compare with the real measurements. The gap and residual between estimates and measurement is monitored to detect pipe burst in Kalman filter-based detection method. This page shows a schematic comparison between traditional SPC method and Kalman filter method. SPC method directly use field measurement after normalization, but Kalman filter-based method has state estimation block between field measurement collection and anomaly indicator normalization block. We confirm that Kalman filter-based method has similarly high detection effectiveness and efficiency under source pipe closure condition compared to the best SPC method, cumulative sum method. Finally, the third study is driven by this research question. In order to increase the level of information for burst detection, we can simultaneously apply multiple different detection methods. Since different detection methods has different pros and cons, such group application provide a room for compensation. However, we are asked to determine the final compromise decision if different detection results are obtained from individual method. We can use OR operator for the compromise decision in which we see there is a burst at least one method issue an alarm. Or we can finally determine a burst only if all the methods issue an alarm. But we need to be smarter than that. So we propose a CNN-based ensemble detection model to extract the final compromise decision. In the model, alarm and no-alarm decisions of individual detection methods are represented by the binary number 1 and 0, which plug into elements of grid image. Each different cell of image has either different method's value or the value of a same method with different parameter. Therefore, this image incorporates diverse detection information and patterns and is used to train the CNN model that has final compromise decision as the output. We confirm that in our result that compare the proposed CNN ensemble model to traditional individual SPC method, the ensemble model outperformed the best SPC method, cumulative sum method. These are summary and conclusion of part 1. SPC method can be applied to consistent operational condition or a small DMA without frequent operational changes. Then we propose NKF-based method to detect pipers even under system dynamic condition. Finally, an ensemble decision model was proposed. Up to now, we saw good example that effective and rapid pipers detection improve the rapidity of water distribution system because we can shorten the time to recovery. Generally, using effective anomaly event alarming software or prompt dispatch of pipe recovery reaction team increase pipe system rapidity. Part 2 is water distribution system resilience and robustness and design using them. In order to overcome the limitation of least cost design that only optimize total system cost, reliability measure has been considered as some safety factor and the second design objective. Reliability is defined as service success probability, which for water distribution system design can be quantified by probability that stochastic pressure satisfy the minimum pressure requirements. Here we have two different networks under the identical set of disturbances. Given a 28 meter pressure requirement, both network has a reliability of 80% because the minimum pressure is satisfied 4 out of 5 times, except disturbances number 4. However, if you look at the pressure behavior in more detail, network 2 has more consistent pressures with low variance of pressure. Therefore, network 2 would be preferred under the same level of reliability. To capture such system performance characteristic, we newly define and propose a robustness index for water distribution system design. Robustness is defined as the ability to avoid or minimize the severity of a failure under disturbances, and it is relevant to persistence of system performance. So the proposed nodal robustness index is computed by 1 minus the coefficient of variation of stochastic pressure. Given many reliability indicator and newly developed robustness indicator, we raised this research question. The first question is how closely these reliability and robustness or performance measures are related, and the second, which physical characteristic of system most affect the performance measure. To answer the question, we performed and investigated two different correlation analysis, Pearson and Spearman rank correlation, for 8 surrogate measure of water distribution system reliability, robustness, performance measure. Those are capacity hydraulic reliability you just saw in the beginning of this part, robustness measure, a reliability measure quantified based on single pipe failure, and finally seismic reliability characterized by multiple component failure condition. Two different versions of each measures are considered to make total 8 measures. In addition, In addition, their correlation with 6 system physical characteristics was analyzed too. Average node degree and machinist coefficients are the system density and connection indicator. Others are total system demand, and that divided by number of sources, and average pipe diameter, and total system area. Total 16 different water distribution networks were used for this correlation analysis. The network considers has diverse characteristics with different layout, density, number of components, etc. This is to derive the generalized conclusion on the analysis. I'm going to briefly show you one key result of this study. This is correlation coefficient matrix or Pearson correlation analysis. Two correlation analysis turns out to have similar pattern of result. We confirm that seismic reliability has high association with robustness indicator. Considering the fact that we have not considered any mechanical failure in computing robustness measure, the proposed robustness is good at considering system persistent performance as intended under catastrophic failure condition. This is summary and conclusion of part 2, but I'm going to skip this. And finally, let's talk about forensic engineering and some future study. This conference is organized by Hyperconverged Forensic Research Center for Infrastructure in Korea University. By ASCE definition, forensic engineering is application of engineering knowledge to the investigation of failure, collapse, and other performance issues of civil infrastructure. While resilience engineering focuses more on system preparation, reaction, and recovery towards and from failure, and solution approach to improve it, forensic engineering is more on the investigation of cause and processes of failure. Those are forecast, detection, simulation, and protection. Therefore, although there could be some overlap in theory, knowledge, techniques between the two, association or inclusion between them can be represented as the Venn diagram over here. In our research center, we deal with forensic engineering in 3 different domains of civil engineering that is geomechanics, structure, and water and environment. Let me briefly introduce our research center here before I'm talking about potential future study. The PI of this project is Professor Jong-Sub Lee, and it is supported by National Research Foundation of Korea for a total of about 7 years. 11 professors from KU, SNU, Yonsei University, and Gyeongbuk National University are together working on this interdisciplinary research topic to develop forensic approaches for failure driven by complex disaster. Those used in 3 domains and approaches based on 4th industrial revolution techniques such as deep learning model, CPS modeling, and water quality monitoring using ROV, etc. These techniques are interconnected for each stage of forensic investigation: forecast, detection, simulation, and protection. Especially group number 3 is water and environmental group, and today is session for this group. We develop forensic investigation approaches for failure that can be occurred at points in urban water cycle. Those techniques are from distributed water management and water cycle, remote water quality monitoring, and up to pinpointing and diagnosis method for pipers, leakage, and anomaly water quality event in distribution network. This is final page of my talk and the most critical potential future study. So the most critical potential future study is related to the fact that smart meters are installing more and more in our boundary. Smart meter data is characterized by pulse data because it is installed at the inlet pipe of each customer. Therefore, it has many zero value for most of time. Another special feature is that it has high temporal and spatial resolution. Some smart meter measure pipe flow rate every second or every minute. It is a lot of information and a lot of room is allowed with smart meter to improve the burst detection effectiveness and efficiency compared to conventional meter generally installed at main line and few locations. More on this will be delivered in Sang-hoon's talk at the end of this session. This is the end of my talk. Thank you for your listening. Thank you.